Okay. This course, the name of the course as you have seen is, I will just write it once again. Actually, it is in two modules. We can say that it is in two large modules. One is sea keeping, which essentially deals with how a ship behaves in waves, or rather one can say motions in waves. Now, by that what I mean is, supposing you consider an ocean surface which will have existing waves, and you take a ship which tries to move, it undergoes all kinds of motions, up, down, etc. Now, not only the motions, as a consequence of the motions there are many effects, such as the bow of the ship might come out of water and bang, water may go on top, there can be large acceleration in one part, and there can be an equipment which undergoes a large pressure, large force because of that. Even human beings are subjected to acceleration, and therefore they tend to fall sick and have motion sickness. All these aspects which are a consequence of the fact that the ship is moving in waves and therefore undergoing motions is a part of sea keeping. So, the first module of the course is basically this part, which we will see later on is connected to essentially the ship motions in vertical plane, that is this way, and about the other axis, the x axis this way. The other part of the course, the second module, which would be approximately half the course, maneuvering, is connected to or related to the behavior of the ship in the horizontal plane. Supposing this page you consider it to be the ocean surface. Now, it wants to turn, make a turn, or it wants to take a trajectory which is zigzag. How will it do that? How would it maneuver? By which instrument or equipment or part of the hull it will it will induce this kind of motions. This entire subject is maneuvering, which is what we will do in the second half of the course. Now, what you will get out of the course is, after the first half, for example, what the course will lead to you is an ability to assess the so called sea keeping qualities. See, this word sea keeping, if I again bring the first one back, the word has come from breaking it as how the ship keeps a sea. Supposing a ship is excessively undergoing roll or undergoing pitch, people would not want to be on the boat. Supposing you have an aircraft carrier, and it could not operate, or aircraft could not land if the deck was undergoing excessive motion. Therefore, one would have to have some kind of a limitation. So, this assessment, is the ship good, can it withstand so much of sea, severity of sea, does the roll exceed certain amount of degrees, etc. All this ability you will be able to do at the end of the course, or at least have an idea how to go about. So, this is the general instruction. Now, having said that, since this course you will see here it is motions in waves, motions of what? Of ships, I can add here, but where? In waves. So, therefore, at the very beginning we require to understand how do you define a wave. Waves becomes the, you might say, my input. I have a surface where I have got waves. I must first understand these waves, which is my environment in which I put my ship. So, therefore, the rest of this today's class and tomorrow's class we will spend trying to recapitulate and summarize how do we characterize what is known as regular waves. So, I will now go to this fact of waves. strictly speaking, one should write this with a additional like qualification, surface gravity waves. Now, by definition, if I have a free surface meaning an interface between water and air, and if I cause a disturbance on the surface, any kind of disturbance under action of gravity, the surface undergoes an undulation, and this is known as waves. This is the definition of waves. Obviously, now there are many kinds of waves. For example, if you went to an open ocean, you may probably find a wave surface looking like that. But before we get there, the first part of the study is, if I consider a single periodic oscillation which gives rise to a wave of this nature that you might have seen many times depicted in many books, many places. This is what is called as regular waves. Now, this regular waves has already been studied before this course as a prerequisite in other courses like marine hydrodynamics, but I need to still recapitulate certain parts. Now, regular waves. We know theoretically that regular waves are studied based on potential theory, which means that the fluid is assumed inviscid and the flow is assumed irrotational, fluid is also assumed homogeneous and incompressible. That means actually this gives rise to this classical governing equation called Laplace equation. As we know, we end up getting where phi is known as the velocity potential. Such that velocity vector q is actually grad phi. This is a very basic definition of irrotational motion, fluid flow in irrotational motion. Now, for surface gravity waves, if you want to study it, turns out you have to have certain boundary condition imposed on the fluid. So, there are so called boundary conditions. There are two boundary conditions that becomes relevant. One is what we call kinematic boundary condition, and one what is called dynamic boundary condition. Now, having gone through all this, it turns out, which is what I will simply recapitulate, that the surface gravity waves potential turns out to be equal to, without proof we are saying, because this is supposed to have been a prerequisite to a course and you would have known that, it turns out for a linear surface gravity wave, the phi turns out to be equal to g a by omega k where, well, this is the kind of solution that comes where let me specify these parts. H is water depth for in this formula, Z is positive upwards, origin is at the mean free surface, that is Z equal to 0 would imply the mean free surface. A is the amplitude of the wave, cos h, yeah right, cos h k h. Okay. So, in this case k is known as the wave number given by 2 pi by lambda, omega is known as the wave period 2 pi by t. Wave here is actually a having an amplitude and the wave profile eta is given by a cos kx minus omega t. Actually this eta is obtained from the fact that it is minus 1 by g d phi by dt at z equal to 0. You can confirm that this, if I do this operation on this, it becomes like this. So, here the wave profile therefore would look like a cos curve, if I were to call this, well it can be actually t, it can be also x, it can be either time axis, which means you are looking at one point, or it can be at a given time x axis. Well, depending on that, if I were to call this t, then the time taken for it to evolve is period t, rather I am going to call this x here, then this becomes my wavelength lambda, this is my a, etc., etc. What it means therefore is, see, is that according to the theory in which we have already made an assumption of smallness of the amplitude with respect to length, which means in evolving this particular, getting back to that, in evolving this theory we had made an assumption of linearity. The word linearity implies here physically that we have said that its slope, that is d eta by dx, d eta by dy, that is its horizontal slope, is assumed to be small. Okay. This was an assumption inherent based on which the formula that the profile is sinusoidal has emerged. So, therefore, what we can say is that the sine profile is a theoretical solution of a regular wave based on the fact that the slope has been assumed to be small. This is what is called as, there are number of terms, it is, we can call it linear wave theory, you can call it ERE wave theory, you can call it first order wave theory, or whatever. So, all these are basically synonymous. All this means that you made an approximation that the slope is small, and if that is the case, then you end up getting a profile given by sine curve. And what is most interesting to see here is that you will find that the phi expression back here is sinusoidal with respect to spatial axis x, that is with respect to the spatial coordinate, and with respect to also time coordinate t. So, therefore, if I were to take a gradient of phi with respect to either time or with space, it would also be sinusoidal, and it turns out all quantities of physical interest are actually gradient of phi. For example, if I want to find out velocity, say v of the particle, it is given by grad phi, that means u is given by d phi by dx, w vertical velocity is given by d phi by dz. If you want to do u dot, that is acceleration, that is d by dt of d phi by dx. If I want to do w dot, horizontal acceleration, it is d by dt of d phi by dx. Other important thing is pressure. If I want to find pressure, the pressure is given by this expression. In here this is my hydrostatic pressure, okay. And this is what is called linear dynamic pressure. Remember, linear dynamic pressure, the word linear because there was another term which was second order, which we neglected according to our linear wave theory. Now you find out that this linear dynamic pressure is gradient of phi in time. So if you were to do this differentiation of my phi curve, obviously all of them is going to be sinusoidal in some form or other. So therefore it turns out that in linear wave phenomena, be it velocity, be it acceleration, be it pressure, everything has a periodicity of frequency omega and time period t. As you know, omega is 2 pi by t, etc. So having said that, this is only the physical characteristic, but one most important thing of the linear water wave which we have not said is the fact that it follows a relation called dispersion relation given by this expression. This is called dispersion relation. Now this is a very important relation as far as water waves are concerned. Why so? You will find out that here my left hand side is omega. Now omega, which is nothing but 2 pi by t. So omega or t, the time period, is related on this side to k. What is k? K is nothing but 2 pi by lambda. That means essentially if for a given water depth h, which means that if for a given water depth I have a wavelength lambda, it is necessarily of certain period t. I cannot have, for example, in a given water depth a wave period of 10 second and 20 second of same length. Now this you can contrast, for example, with electromagnetic radiation, where you can have different wavelength, different frequency, but there is a speed is constant. We will find out here that now what is my speed of a wave. See, when I have this wave here, next instant it goes like that, next instant it goes like that. The form of the wave is travelling. In fact, I can show that if I were to write this eta to be a cos k x minus omega t, this can be written as a cos k x minus omega by k t, and you will see that if you are to travel at the speed omega by k with respect to this wave, to you it will look stationary, which essentially means the form is travelling with the speed omega by k. So omega by k becomes my phase speed, or some people call it celerity. And it is interesting because omega by k is nothing but lambda by t. If you see, because omega is 2 pi by t, k is 2 pi by lambda, and obviously it makes sense because what is happening is that this is lambda and the time for it to the form to actually go down one cycle and come up, which would imply as if this has gone here, is t. So therefore you would think this form has travelled from here to here in time t. So this is what is phase speed. Remember, it is the form that is travelling, not the particle itself. We will see later on that the particle here, they move in a circular fashion. We will come to that in a minute. Now having said that this omega square etc., now I will actually come to one simplification. What is happening here, you see that in this expression, this is all for water depth h. Now in if, so for example, h was very deep, in other words kh is like 2 pi by lambda into h is very high, tan h kh will tend to actually 1, like this relation, this gk, this tan h kh, this will tend to actually 1, and even this relation will all simplify. In such cases, what happens, my relation, this relation becomes omega is equal to gk. Okay. And in fact, these relations in fact all become exponential kz, e power of kz minus kz. So, in deep water, when I assume h tends to infinity, then kh obviously tends to also infinity, because you know kh is 2 pi by lambda into h, then tan h kh tends to 1, because tan h kh actually if you write x here, tan h graph looks something like that, it goes to 1, that is tan h x. And there are similar relation for sin h and cos h x for large values of x. So, if I put those things, it turns out in deep water, well, the word deep water implies for h tending to infinity. For now I am saying this, but we will now find a practical limit of what is h in a minute. It turns out phi reduces to g a by omega e power of, well, actually this will come depending on which side the z is, well, z is plus opposite, so therefore it is plus kz, and of course eta remains same, and my dispersion becomes omega square equal to gk. Okay. Now, this is another thing that I will like to tell you here. Let us look at this relation. You will find here two things. One is that phi is a function of x sinusoidally, is a function of z exponentially, and function of t sinusoidal. Okay. So, therefore, what is happening when I differentiate this, number one is that it always remains sinusoidal, because when I differentiate it, supposing I differentiate it with respect to x, it is sinusoidal. If I differentiate with respect to z, also it is sinusoidal, because this does not get differentiation. If I do it against t, also sinusoidal. But other thing is that its z dependence is exponential. That means that if I were to see a property of a water wave along z, every property is reducing sinusoidally, and every property is harmonic in the horizontal plane, whether it is with respect to space or with respect to time. This is very important, because we will find out afterwards, then when I put a shape here, obviously it would also respond to this harmonic excitation, you know, like something is being pushed every 10 seconds. So, it will also have that every 10-second oscillation. So, this is extremely important from water wave, that things come down exponentially. How does it come down? With e power of kz. What is kz? E power of 2 pi by lambda into z. Now, it turns out that normally if lambda, or rather I will tell you, if z is more than equal to lambda by 2, then e power of kz, that is becomes e power of minus, well, minus z I will say, because z is plus opposite, minus pi. Okay. This value itself is something like 0.04, and normally just like when we say, you know, the sin theta is theta if theta is less than 4 degree, similarly we will say that normally when e power of the exponential part has become more than e power of minus pi, it is almost 0. So, the rule of thumb is that is how this word came, that if water depth is more than half the wavelength, then anything that is happening below that is so small, almost 0, that you can ignore it. So, we therefore we say that if water depth was more than half the wavelength, we consider the water depth to be deep water, or it is a deep water case. Okay. On the other hand, if the water depth is less, of course, that would not hold. In fact, we call that to be intermediate water. Now, why I am saying this? Because in our course of seakeeping, normally we always deal with deep water cases. Why? Because a typical wavelength would be about 100 meter, 200 meter, 300 meter, maybe 400 meter. But ocean depth, where ships operate, runs in thousands of meters. So, mostly the operation of ship would be in deep water, whatever the water is. Therefore, rest of the course when we talk we will only consider deep water cases, because ship operate in deep water when we are looking at ship. You can always refer to the exact equation with H, but it is an unnecessary complication. There is no point of doing it, because when you actually put numbers it will turn out that e power of kh, tan h kh will become almost 1, 0.9999 something. Okay. So, having said that, this is my property of water wave. Now, I will try to tell you about the particle velocity, etc., etc. Well, before that, let us now spend little more time on dispersion relation still. So, I have this omega is equal to gk. Now, speed c, what is c? C is omega by k. So, that is g by omega. Okay. Now, g by omega is what? G by, now you see it is g by omega means speed depends on frequency inversely. So, if I want to write omega as t, then it will become 2 pi by t. So, therefore, speed depends on period, but if I want to write in terms of length, g by, see omega I can represent as root over of gk, because omega is root over of gk. So, this will turn out to be root over of g by k, it is root over of g by lambda by 2 pi. So, what do I find? C varies with root lambda, C varies with 1 by omega, C varies with t. Okay. So, this tells us that celerity of water wave or phase speed depends on length, and of course, length and frequency are connected. Therefore, it depends on length or period or frequency, which means for in deep water, if I were to tell omega or t or lambda or c, all of them in deep water and also in shallow water for a given h would immediately relate to each other. There can be only one value for this and this and this and this. So, you cannot have, for example, two different wavelengths travelling at two different speeds. This is where I was earlier mentioning water waves differ from electromagnetic radiation, because in electromagnetic radiation or in sound waves, for example, C is constant. For example, in sound waves, if C was not constant, you probably would not hear me, because various frequencies would have reached your ears differently. If the electromagnetic radiation was not of same speed, you would not see the picture white, because all colors would be different, but in water waves it is so. So, this is why water waves are called dispersive, because if 10 water waves start of 10 different length at one point, then eventually the longer one would have travelled this much, shorter one, longer one would have travelled farther. So, it would have separated out. This is what we call dispersion relation, very very important relation. And what happened now, coming back to this this part, this phi, we are writing this C G A by omega. Some people will write in terms of some other parameter, because I can now write omega in terms of t, in terms of lambda, in terms of k. So, there this part can be rewritten depending on what parameter you want to use as independent parameter. It can be something like Ga by, well, root over of Gk. For example, I can write Ga by omega as Ga by, well, not in this case, in the deep water case, Gk, so root over of Gk, and I can relate that root over of G 2 pi by lambda a, etc. So, this is a question of only convenience of how we proceed. It really depends on the way we want to look at it. Okay. Now, let us look at some of these numbers, therefore, like relation of this number. Now, typically let us say, let us take a wave period of t. Okay, before that, let me also see this other way around. Now, lambda, it turns out therefore equal to 2 pi g by omega square. This is from the dispersion relation, omega is equal to gk, straightforward. So, this, because we are trying to relate now a relationship, this turns out to be, if you were to put a SI unit, that lambda in meter, g is like meter per second square, and period t in terms of second, actually this I can write this way, g by 2 pi square by t square. So, this turns out to be gt square by 2 pi. So, this in that this thing becomes almost 1.56 t square in SI unit. So, that tells me that if t was 8 second, lambda would have been 8 square into 1.5 around 100 meter approximately. If t was to be 10 second, lambda would be around 150 meter. Say if t was about 12 second, lambda would be approximately 144 into 1 and a half, about 200 or so, let us say. It is all approximate number. So, this gives me a feel about the relation between this number and this. Let us look at the speed value. Say for this, what is the phase speed? Very simple, 100 by 8, because lambda by t, it would have been something like 12 meter per second. Here you will see 200 by 12, it would be approximately 16 meter per second. So, you see speed is increasing. This is of course the reason why a long waves like tsunami, you have travel speed so high, phase speed of travel so high, it can be in many kilometers per second per hour. So, this is exactly the part connected to dispersion relation. Okay. Now, I will just want to also tell about the particle path that it takes. It turns out if we were to do a study in deep water, these particles actually travel in a circular way. This is in a circular way, and obviously since I mentioned earlier that everything diminishes with this thing, in here the particle will move this way, in here the particle will move this way, etc. So, the particle motion is basically circular path. That means, if I were to put a particle here, it actually stays in same place going like that, it does not move forward according to linear theory. So, there is no net mass moving forward as per linear theory, it is only the form that is moving forward. So, the particles are just moving like this. You can also get a feel about the particle velocities for the simple reason that, see, this is a, this circle distance is 2 pi a, and a particle is travelling this 2 pi a distance on an average in period t. So, therefore, 2 pi a by t would be the kind of like speed. Now, one thing in dispersion relation that is very important is that we come back to dispersion relation is because, see, this vertical axis which is my a, this has no connection with the dispersion relation. I could have another wave this much or another wave very small, all of them will have same frequency omega, length is same. So, these two are connected, but for the same omega lambda combination I can have different A's. So, in other words, the dispersion relation is connecting my quantities in the horizontal axis, time axis and x axis, but nothing in the vertical axis. In other words, if I have an 8-second wave, it is 100 meter. What is the height? Well, 100 meter wave can have a height of 1 meter, can have 2 meter, can have 3 meter. This is not specified. Why it is so? Linear theory, because remember that I have made an assumption that, well, eta x, eta y is small. What is this? Approximately they are equal to a by lambda in that order. So, what is happening? A by lambda has been taken as small, but no specific value of a. What is small? 0.01 can be small, 0.02 is also small. Therefore, if I take 0.01 for example, my a would have been certain number, 0.02 would be twice the number. So, a cannot be specified. So, the theory applies for small a as long as a by lambda is small, but not for any specific value of a. This is very important to understand. Okay. So, now the next point, very most important point, is actually to talk about is pressure. The other part of water wave would be pressure P. Now, what did we say before? P is minus rho g z minus rho d phi by dt. Okay. Now, let me write the phi expression again, because this is important for us to realize this. It was g a by omega e power of k z I wrote area sin k x minus omega t, right. Now, how much is rho d phi by dt? Let us work it out. See, minus rho d phi by dt, that is linear dynamic pressure. If I do minus here, so this 1 minus, let me just write it down, this becomes minus omega, right, comes in g a by omega that is right. So, that means it is minus g a e power of k z, no, yeah, okay, cos k x minus omega t, etc. Now, what is happening? Obviously, you can understand this, that again, now if I see this eta, it is something like a cos k x minus omega t. So, naturally there is a highest dynamic pressure, either positive or negative, occurs under crest or trough for this. But remember, in all this formula, my z is 0 here. Okay. Now, let us look at the two part of the pressure by a plot, the hydrostatic pressure and the linear dynamic pressure. Now, let us look under trough. So, I have got here, say, now under this, see, remember this is Z0. How does the hydrostatic pressure vary? Well, it is minus rho z z, okay. Z is negative down. So, therefore, this becomes positive here this way, giving a pressure, you can say this is positive pressure, right. Obviously, pressure can be positive, but the interesting point is that what is happening here? Well, you end up getting a negative pressure, that does not make any sense. But anyhow, let us put this way, you end up getting here rho z z, that is static pressure, to be a minus rho g into a at this point. Okay. Now, what is my dynamic pressure? You will find out that if I were to work, this is also, well, see here, actually there is a rho here, that this rho has to be there, this rho here, this rho here. So, this will be also rho g a, because z is 0. So, if you work it out here, it will turn out to be like this, exponentially down, and this much is rho g a. Okay. Everything is fine. Remember that we have defined in our theory, and that is the most important point when you are doing this application. My z is 0 at this level. This is my z equal to 0 level, and my water is only below z equal to 0. My water is assumed in theory only z equal to less than 0. This is my fluid domain. However, please understand this, that I have now a crest here, means this part is water, but my theory I always have only, is valid for z equal to less than 0. What happened here? I want to know physically what is the pressure at this point, for example. How do I find out? Let us say this is 5 meter, I want to find out what is my pressure 1 meter below the crest. Now, if I were to apply only rho z z by this formula, what do I get? A completely absurd result of a negative pressure. No, that is not, but it is, that is true, but then this wave is of course existing there. See, the wave is existing because the particles are moving. Liquid cannot sustain shear. The question that is asked is perfectly correct, provided there was no motion there. See, obviously, if you look at the wave, it is sustaining this shape. It is of course sustaining the shape. If it did not sustain the shape, I would not have a wave. Why it is sustaining the shape? Because the particles are moving. So, there are dynamics involved, and this is the question. You cannot presume this mass of water to be hydrostatic, and if I take an hydrostatic pressure, I end up getting minus rho z z. That is okay, that absurd result come because hydrostatically it is absurd to consider that water mass can stay like that. It can only stay along with the hydrodynamics. So, now if I were to add the dynamic pressure, there is also a problem. Supposing I add dynamic pressure, so I apply this formula. So, what would happen? It goes like that. Say z e power of k z, z equal to plus 1 whatever. Now, if you look at this point, what would happen? This obviously is more than rho g a now, this is rho g a. So, this will end up getting some pressure. That is not correct because my pressure at this point is supposed to be 0. Where is the anomaly? The anomaly is because that in developing linear water wave theory, what we have said is that this height with respect to the length is very small. A consequence of for that was that every quantity that is on the surface is assumed to be same as it is on the z equal to 0 line. That means, if I were to take a point here and if I were to take phi at z equal to eta, this is taken same as phi z equal to 0. Okay. Now, obviously, you look at the pressure, what is pressure here? d phi by dt at z equal to eta, but that I have said is same as d phi by dt at z equal to 0. That means, I have said the pressure in this region, dynamic, all the dynamic quantities are same as this, which means I made a presumption that this actually pressure is like this. This pressure is constant in this region, and if I were to do this, then there is no problem, because now if I add this line with this line, what do I get? I get a pressure here this way, because you see here up to this much, if I add this black line with this line, I get the pressure here, and here I get the pressure like this. This is how much? This is nothing but this plus this, that is this much plus this much gives you this much. Okay. So, then this is exactly how the pressure varies under linear water wave. Now, this is extremely important for us to understand, because you see you must have a physical pressure here, and the pressure, dynamic pressure is varying like this. Once again I will repeat this, whereas hydrostatic pressure is varying like that. Now, if I were to evaluate a pressure in this regime or anywhere under wave, you cannot use hydrostatic pressure by itself, because if you did that you end up getting a wrong result. But if you were to find pressure, you have to use hydrostatic and hydrodynamic pressure simultaneously. Supposing I want to use hydrostatic pressure, as you have done sometime in ship strength. In a ship strength, what we do, if you recall, you simply take a ship, you have this profile and you find this buoyancy curve based on this buoyancy. Okay. That means you are using only hydrostatic pressure. What here you can see is that, supposing I use this my datum line, this was my z equal to 0, what would have been my hydrostatic pressure? It would have been like that. Well, this is closer to, see now if I were to see this color, this line is 1 and reality is this and this. So, at least this is not that bad, in the sense that you will not go completely off, you are going to make this much of over prediction, fine, but you do not go completely off. Okay. So, if you use only hydrostatic pressure. So, you know that if you are to use only hydrostatic pressure, then you must use, you cannot use rho z z with z equal to 0 as the mean line, then you must use an instantaneous water surface. I will give an example of this with respect to a boat now in a minute. See, so we end up finding this, that if I was to have this thing, the pressure is basically coming like this is my pressure, actual pressure, and if I were to ignore the dynamics and I used this as Z0, then my pressure would have been this. Now, you think of this a boat, what happens? Suppose there is a boat here. Okay. Now, what happened? Well, let us consider it in a calm water first, the boat. It has a draft of T, okay, which means that below T I have this pressure rho g T supporting it. Now what is happening here, you see, or rather I should make it bigger, see, draft like this much, see. Now thing is that in this case what happened, tell me, will the draft go down or go up under crest? What would be the situation? Remember that you see that the draft would have been same if the pressure was this much here, but actually my pressure is this much. So what would happen? The body would actually sink down in crest, because I must have the pressure equal to this much to support that. Yeah, okay, I will explain this picture again once more. Okay, now perhaps I will take a better diagram once again, because this diagram, I will take this case here. Red line. See the pressure, actual pressure under wave under a crest looks like this. This is my straight line, and actual pressure looks like that. That is my actual pressure. Now I have a boat which has a draft of some value. What does it mean? It means that in this here I had a hydrostatic pressure of rho g into T, which supported my mass. So I must go down that much where my pressure is rho g T. It is a flat bottom plate, because obviously I must have as much draft wire here, because only this face is contributing to my buoyancy in this case. Now here what has happened, I have this body. Now you see here, in this case my draft here is this much, but my pressure, this is my T and this is my rho g T, this much. So if the pressure was this much, my draft would have been T, but actually my pressure is only the small line. So my rho g T pressure would come when this bottom surface is here, which means the body must actually come down, because the pressure below the crest have reduced rather than increased. So therefore the ship must come down further in order to support itself. Okay, and the opposite would actually happen in trough. So therefore what would happen, of course this actually happened in a very small, the numbers are not so large, but there is a tendency for the draft to come down and go up more because of the hydrodynamic contribution, dynamic pressure contribution. So the dynamic pressure has therefore a extremely important role to play. Now why we are interested in dynamic pressure so much more? Now let us look at this in the same case also, hydrostatic balance case. Ultimately I want to find force. For any dynamic system I would like to find out the force, the net force acting on the body, because the entire module C keeping is because to study what the waves does to the structure. What does it do? Well, in a hydrostatic case, if there is a body there, it gives you hydrostatic pressure, that gives you buoyancy, and that is what keeps it afloat. Everything is based on that. Now in a dynamic case the same thing, I actually have to find out what is my pressure. Well, what is the force? And force is nothing but integration of pressure over the surface. So I need this pressure very well, and therefore I need to find the pressure very well. Of course the fact that if there is a body there, the wave itself would change is a different issue altogether. We will come to that afterwards, but the fact that even if I did not assume that, we still have to figure out the pressure under wave, and therefore I need to have a very good understanding of the pressure, and if I do not take the Z etc. properly, I end up getting pressure wrong. So if I were to only use hydrostatic pressure, I will repeat again, you must use Z0 to be the variable axis measured from the instantaneous water line. If I was using a theoretically consistent value of Z0 to be the mean water line, then I have to use hydrostatic and hydrodynamic pressure together, not in isolation, because in isolation any of them cannot exist. this is one of the most important part that we end up finding here. Okay, now let us see. Now the similar thing would actually happen in a trough case. If I were to look at the trough case, like, let me see this trough case here. Here this pressure is opposite. See, this was like that coming, whereas the other pressure, well, this is A part here, it is this side. So you have to actually now add these two. So therefore the situation become different, and there what would happen is that, see here again, if I were to see, remember there is no water here, this part, let me just see this. See here, essentially what would happen, therefore this and this will make it 0 here. So I will end up getting, if I were to have this part, but with this respect I have this added, so I will end up getting this minus this, because this is on the other side, will end up getting some value like that. So what I mean is that again the similar kind of thing will occur, like in trough, like in crest. The only problem that happens here is that because there is no water here, you do not have to really consider, because this region there is no water. Now I tell you why these things are important, because we will find out that in many case of floating body structure, ultimately you will have to find the pressure over the mean water surface, even though the water is like that. Theory will tell us that we have to determine on the mean water surface, and that is why it is always good to know the pressure and use a consistent theory of z equal to 0 on the mean free surface. If z equal to 0 on the mean free surface, then you will have no problem. So for our study purpose, we would always take z, this thing, this is x, and this is my z equal to 0, that is z equal to 0 will be always my mean surface. Okay. So essentially today I will in fact close on this pressure part, and we will, next lecture we will have one more lecture on linear water wave theory. We will discuss about the other aspects of energy, energy flux, group speed, etc., and perhaps we will also work out some simple elementary calculations, how these numbers are used to determine. You can actually see from here itself, as an example, this speed, as I said, c is equal to omega by k, and the way we have done is omega by k is 2 in terms of like let me see, time, it was something like 2 pi by t, and omega square is gk. So well I was trying to write it in terms of time. Let me just figure it out. Just no, that's okay. See, c is omega by k, omega square equal to gk. In any case, you can relate that c to be in proportional to something like t, that we have done at some point of time. So what I am saying is that now, if see, it turns out that if t was 8 second, my lambda was 100 meter, and c was about 12.5 meter per second. But you will see that if my t is equal to, say, a tsunami wave, 20 minutes or 30 minutes, say 30 into 60 second, you work out lambda, you will find out it will turn out to be order of several thousand kilometer, and you will find out c will turn out to be in order of something like 100 kilometer per hour, 500 kilometer per hour. This is exactly why the speed is high, but people do not realize, and you must realize, and I will tell you, I will end this talk with this, that wow, how do you explain physically so high c? What is the meaning of this so high c? How do you physically see? The reason is very simple. If the wave is very long like that, let us say this is actually say 100 kilometer, what happened after 20 seconds, this water has come down here and this has moved up here. So, water did move out from here to here in 20, the form appeared to have moved up from here to here in 20 minutes. So, after 20 minutes this place would appear to be having a trough water. So, this it is like an oscillation. So, this oscillation was like this at one time, next instant it become like that. So, you see what happened, this water appeared to have moved to this place, and obviously if there was a coastline here, you will suddenly find out 20 minutes water has moved up and rushed in. So, therefore, the concept is on the form only which can travel very fast, like a long line, you just shift it this way. So, this much distance, this is moving in that time. Okay, this is how you explain, never the particle moving. Particle cannot move 100 km per hour. Anyhow, so this is about the speed. We in our course we will find out that our range of wave speed will lie between something like 5 seconds to maybe 20 seconds. We are not interested in tsunami, we are not interested in capillary wave. None of them have any effect on the ship. We will close today's talk of this and begin tomorrow on the other aspect of water wave theory. Thank you.